Hello, everyone, and thank you for joining us today to learn about emerging pictures of distant worlds with Professor Bruce Macintosh. Bruce Macintosh is a professor of physics and the deputy director at the Kavli Institute for Particle Astrophysics and Cosmology. He is also the principal investigator of the Gemini planet imager and leads a science investigation team for the coronagraph instrument on the forthcoming Nancy Grace Roman telescope. Bruce also co-led the team that took the first ever picture of a solar system orbiting another star. Please join me in welcoming Professor Macintosh.
Thanks for the opportunity to talk to everyone. I hope everyone is as safe and reasonably sane as is possible under these complicated and challenging circumstances. And I'm glad I have a chance to talk a little bit about a distracting topic, like what we're learning about other planets and other solar systems. The questions we're trying to grapple with are ones that humans have been thinking about for most of human history, for literally thousands of years. Are there many worlds in the universe, or is there but one? And we actually know now part of the answer to this question. Astronomers have detected more than 4,000 planets orbiting around other stars. I'll talk about them. What we don't know is how many of these planets are like Earth. Is the Earth, with its perfect atmosphere, with its life, with water on its surface, unique? Or are planets like Earth common all through the universe? We don't know the answer to that now, but we're approaching the point where we can. The technology that astronomers have developed and deployed and will deploy on telescopes in space over the next decades are going to allow us to answer that question. I'm going to talk about the road to how we answer that question, the ways we study planets now, and a little bit about the future. So again, going back 2,000 years, our picture of the universe was fairly simple. There was the Earth, and there was a bunch of stuff that wasn't the Earth, and everything that wasn't the Earth orbited around the Earth, unsurprisingly. It's sort of a natural. We all think we're the center of the universe. The problem with a model where we're the center of the universe is it gets incredibly complicated. If you want to predict the motions of the planets across the sky, they can't just go around the Earth. They have to go around the Earth in complex zooms and curlicues, this kind of dance of planets you see on the left. To ordinary people, that might be okay. To scientists, it was really unsatisfying. And so there was a revolution where Copernicus, Tycho, and Kepler, people like that, put together a model realizing that the Earth didn't have to be the center. Instead, the sun would be the center of the universe, planets would go around it. And they proved that to other scientists with math. This model allowed you to predict, say, where Mars was going to be next month, much more accurately than the old-fashioned Earth-centered model could be. And so Kepler wrote a large book about it. There's actually copies of it you can see in the Special Collections Library at Stanford when we're allowed to go there again. And to the satisfaction of other scientists, it proved we were not the center of the universe. But predicting where Mars is going to be next month was not actually a very compelling approach to change the viewpoint of the rest of everybody in the rest of the world. Meanwhile, Galileo, one of the first astronomers working with telescopes, also showed that the Earth wasn't the center of the universe through a much more visually compelling method. With his very first telescope, on one of his very first nights, he looked at Jupiter. This is sketches from his notebook. And when he looked at Jupiter, he saw dots next to it. The next night, he saw dots next to it. And the night after that, he saw dots next to it and realized that those dots were moving. They were orbiting around Jupiter. Everything didn't have to orbit around the Earth. Jupiter had moons. The Earth was not unique and special in the solar system. And it's interesting that that display where you could actually look through the telescope and see something with your eyes and realize it wasn't the center of the Earth was what caught the attention of the religious authorities of the time, who were kind of invested in this idea that we were the center of the universe. And of course, that's what got Galileo in rather a lot of trouble. And it's a bad sign when scientists compare themselves to Galileo, so I'm not going to do that, at least at this time. But what we do is make pictures of planets. We try to see other solar systems the same way Galileo did when he saw the first system of moons around another star. Okay, when Galileo and Kepler and so on were studying, our solar system had 6 planets. Briefly, it had 9 planets. Then we changed the definition, so we're back to 8. And in our solar system, we see this kind of clear hierarchy. There are planets that are close to the sun. They're mostly made out of rock. There are planets that are far from the sun. They're giant and gaseous and puffy. And there's little things floating around like Pluto and its various brethren. And when I was in graduate school, we were taught that every other solar system would look like this, that the process that formed our solar system was universal and that we had to be typical and representative. And in hindsight, that again turns out to be, it's not quite as embarrassing as Ptolemy thinking that we're the center of the entire universe, but it's pretty close. As we've discovered planets, they've been nothing like our own solar system, and astronomers have been grappling with that knowledge for the past 20 or 30 years. So how have we detected these other solar systems? The first approach that's been used is the Doppler technique. So seeing other planets is really hard. Jupiter in our solar system is 10 to the 9 times fainter than the sun. I'll talk about how we can overcome that later, but to begin with, we didn't have the technology to do it. Instead, we look for evidence of the planet indirectly. So we talk about planets orbiting the sun, but what really happens is both the planet and the sun orbit each other. Newton's laws of gravity tell us that as the gravity of the sun tugs on a planet, the gravity of the planet tugs back, and they both pivot around a point in the middle, something we call the center of mass. And that means that even if you couldn't see the planet itself, but that you could see the star, that little wobbling motion of the star would tell you there was something invisible and massive causing the star to move. And from the laws of physics, you could determine whether that was a planet or not. How do you tell that the star wobbles? You can't actually see it wobble back and forth in the sky. The tiny motion is too small for even our best instruments to detect. Instead, we measure the light from the star and see something called a Doppler shift. As the star moves, as it comes towards us, now it's moving sideways and then it's going to move away from us. The color of the light from the star changes very slightly, the same way the pitch of the whistle of a train changes as it moves compared to you. The motion is tiny. In our solar system, the sun moves about 7 meters per second due to the presence of Jupiter. But with modern telescopes and spectrographs, we can detect that. So the very first extrasolar planets known were seen through this method. And when it happened, a whole bunch of them were discovered in 1995, 1996, 1997. There was this huge rush of amazing and important discoveries. There were, of course, press releases with these pictures of planets. This one has a moon that appears to be evaporating because it's very close to its star. But of course, that's not what we saw. We didn't see planets. We just knew that something with gravity, which we guessed was a planet, was present, and that was tugging the star around and around and around and around and around. What we really saw was this. Wiggles on a graph. We saw that the velocity of the planet was changing versus time. It's still an amazing discovery, and it was actually recognized. We saw that it would take about 4 days for the star to move back and forth, which is important in a way I'll tell you in a second. It was an amazing discovery, and it was actually honored with the Nobel Prize for Mayor and Queloz, the Swiss astronomers who made this first discovery, got the Nobel Prize last year. But what it told us basically was that there's something that's kind of a planet there and not much else. And what astonished us was the kind of planets they found. The gravitational signal was as big as a planet as Jupiter. These were giant planets, which is what their equipment let them say. But the planets were whizzing around their star incredibly close to it, taking only 4 days to orbit it, practically grazing the surface of the star. One thing like that could be weird. Maybe it wasn't really a planet, but rapidly they discovered dozens, and now we know of hundreds of what we call hot Jupiters. Planets that are incredibly different than our solar system. There's nothing like that close to the sun in our solar system. In our solar system, the only giant planets are cold in the outer parts. The second way most extrasolar planets have been discovered now, the dominant way, is by not seeing the planet's gravity, still not seeing the planet, but by seeing its shadow. If you have a planet orbiting a star, as I said, you might be able to detect it through Doppler techniques, but if it lines up just right, it might eclipse the star. It might pass in front of the star, and for a few hours, the star would get a little bit fainter because planets are opaque. They absorb the light that comes from the star and make it undetectable. For that to happen, you have to get incredibly lucky. The planet has to line up just so. Although if the planet is very close to the star, you don't need to be quite as lucky because the odds of it lining up will go way up. It'll get, for a Jupiter-sized planet, about 1% fainter, which doesn't sound like a lot, but actually you can detect in your backyard, literally, with a modern digital camera and a decent telescope. With precision telescopes, we can detect changes in light due to much, much smaller telescopes. And in particular, through NASA's Kepler Space Telescope, this has been the main way we've discovered extrasolar planets for the past decade. Kepler, of course, to find a planet this way, you have to get incredibly lucky, has to line up just right. The way Kepler deals with that is it looks at 100,000 stars at once so that some of them will be lined up in exactly the right direction, carrying a multi-hundred megapixel camera into space. Kepler shut down a couple of years ago, but before it finished, it continued this revolutionizing of our picture of other solar systems. This is an animation a colleague of mine put together showing some of the planets detected. This actually just shows the systems in which Kepler saw more than one planet. And there were, as I said, hundreds of them, but all still incredibly different than our solar system. You can see our solar system on the right, big and spread out. All of these other solar systems were compact. They're dense, packed with two or three or four or five planets right next to their star, and full of planets that seem very different than our solar system, that are in between the giant planets and the little planets. On our sort of cartoon where the Doppler planets were here, Kepler planets tend to be here. They're sort of 2 or 3 times the size of the Earth. They're closer to the sun than the Earth is. Understanding what these planets that we call super Earths or mini Neptunes are remains one of the big puzzles in modern astronomy. Kepler was intended to answer the question about whether there were planets like Earth, but it didn't quite. Especially, we wanted to answer whether there were planets in what we call the habitable zone or the Goldilocks zone. That's the area in which you could potentially have conditions like Earth, liquid water, reasonable atmosphere. For that to happen, you have to get just the right amount of sunlight. If you're too close to the sun, you can roast like Venus. If you're too far from the sun, you freeze like Mars. If you're in between, you can be habitable just like Earth. That's why we call it the Goldilocks zone. But of course, a planet in the Goldilocks zone in our solar system goes around the sun once every year, like the Earth does, which means if you're seeing transits and eclipse, you'll see them once every year. The primary Kepler mission only lasted for 3 years, and so it could just barely see maybe 2 transits from an Earth-like planet. Combined with the fact that these measurements are really hard, it had essentially no sensitivity to planets just like Earth, no ability to see planets that could have life and liquid water on their surface. Around stars like the sun, on the other hand, if you have a star that's red and faint and cold, and there are lots of stars like that out there in the universe, to get the right amount of sunlight, you have to be huddled up closer to it, more in the Venus region or even the Mercury region, which makes the planet much easier for Kepler to discover. And so Kepler and its successor missions and ground-based telescopes have discovered a few planets that are kind of Earth-sized or a little bit bigger and are in this habitable zone. And those generally tend to get advertised as being discoveries of planets like Earth. NASA loves them. They have press releases. The press releases have pictures. You can see there's clouds on this one. It's a bit deserty, but maybe there's some oceans. And although nobody says, oh, there's life on it, in the back of everybody's head is the idea that it may have some kind of life present on its surface. But again, that's not what we know. What we know is just there's a planet there and it's a certain size. Could have oceans and foxes on its surface. It could be a mini version of Neptune with clouds of hydrogen gas. It could be made of cheese, although that's astrophysically unlikely, all things considered. A colleague of mine, Mark Marley, likes to say every time there are headlines about Earth-like planets, that a planet is Earth-like in the same sense that distant headlights on a desert road or 1968 Mustang-like. Could be a Pinto. All you know is how far apart those two headlights are, how big the object is. You know nothing about what it's composed of. Which is bad because unfortunate because composition provides clues in our solar system as how planets formed. Our sun, for example, is mostly hydrogen and helium and only a tiny bit of other stuff. Jupiter has more other stuff in it because we think Jupiter formed out of a mix of solid material and sun-like material. Uranus and Neptune, even more solid material. And of course, the Earth has essentially no hydrogen and no helium and is entirely made of solid material. And the process that formed these led to planets like the Earth. If we could measure the composition of even the Jupiter-like planets, that could start to provide clues as to whether the process that formed the Earth is a universal process and whether there are other Earths out there. How do we do that? We use something called spectroscopy. You may remember from chemistry and physics classes, every object has a distinct spectrum, has wavelengths of light that it preferentially likes to emit or absorb. Sodium, for example, emits 2 distinct yellow spectral lines, produces the yellow glow of sodium streetlights if you have them in your neighborhood. Neon makes brightly colored lines in old-fashioned neon signs, etc. If we can study the spectrum of light, that can tell us what atoms are present. If we see those 2 yellow colors, we know there's neon. If we see a forest of color, we know there's sodium. If we see a forest of colors, we know there's neon. And so by studying the spectrum of other planets, we can learn what they're made of. For transiting planets, even though we can't see the planet itself, we can just barely do this in some cases. As the planet passes in front of the star, mostly it blocks the light from the star, but right at the edge of the planet, some of the light will graze the planet's atmosphere, make it through the atmosphere, reach the Earth, where our telescopes will let us measure what chemical compounds are present in the atmosphere. And for some of the planets that have been discovered to transit, mostly just giant planets so far, that has been done. Because this is a Stanford talk, I'm allowed to show graphs, I'm told, so I'll show maybe 3 total. This is a graph of how strong the signal from the planet is with different wavelengths of light, and without going through all the colors and error bars and things like that. When this planet was studied by a team led by Hannah Wakeford, they saw evidence of clouds in the planet's atmosphere at short wavelengths. There's no chemical signature because the clouds are blocking the light. And at longer wavelengths, they saw a signature of water, which sounds really exciting until you realize the planet has a temperature of 700 degrees and is the size of Neptune. So the water is like superheated steam in its atmosphere, but shows that we can begin to study their composition. That works right now still for giant planets. They're still mostly hydrogen and helium, but with some evidence of more of other stuff. But we're also still seeing just a very biased sample of planets that are close to their star. And I should say in the near future, the James Webb Space Telescope, which we hope is going to launch at the end of the year, will be able to do this for smaller planets. Still not Earth's, but maybe in this Goldilocks zone for the lower mass stars. But now let me talk about what our group does. So what we want to do is study planets in a whole different way. We want to study the outer parts of solar systems, and we want to learn what they're made of, and we want to actually see a picture of the planets. The problem is, like I said, that's hard. Looking for a planet is like looking at a lighthouse and trying to see a firefly next to it, something that's 1,000,000 or 1,000,000,000 times fainter than the source of light. Incredibly challenging, but actually possible with modern technology. The first reason it's challenging is because we mostly do this with telescopes on the Earth's surface. The problem with being on the Earth's surface is we have the Earth's atmosphere. I mean, it's kind of a feature because you'd like to keep breathing, but it's also a problem because it blurs images. This is an image of a star taken a fast ultra magnified image of a star taken with a telescope on the Earth's surface, and the atmosphere blurs it into this distinct blobby mess, which of course would make it impossible to see if there's a planet next to it. How do we deal with that? And this is an image of the planet Neptune seen from the Earth. Again, blurry, blobby. We use a technology called adaptive optics that I've worked on for most of my career. We take the light from the telescope, and rather than focusing it on a camera, we focus it on a deformable mirror, a mirror that can change its shape 1,000 times a second or so. Then the light that's bounced off the mirror that has been refocused is sent down to a scientific camera or to a wavefront sensor that uses a computer to calculate what shape the mirror could take. It's complicated technology. It's not easy to make it work, but when it does, it can correct for what the atmosphere does and make Hubble telescope quality images or better from telescopes on the surface of the Earth. And for example, it could take that blurry image of Neptune and turn it into something like that. So we can reach amazing levels of image quality. When we apply that to a star is indeed a little tiny sharp point. Maybe you could see a planet. So we turn the exposure time up on our camera to look for planets near it, and we see a mess like this. What we're seeing is things like polishing errors in the telescope itself. The telescope's mirror isn't perfect, and turbulence that we didn't fix correctly. It's basically the equivalent of lens flare. If you try to take a picture pointing into the sun, hard to see anything. Even with the adaptive optics, still not enough to see a planet like Jupiter. And so we cheat a little bit. We don't look for planets like Jupiter. What we look for are planets that are young. When planets form, a lot of energy gets released, which means the planet spends the first 10 million years or so of its life hot enough that it glows at infrared wavelengths, which we can detect with infrared cameras and make the planet that much more detectable. And so with collaborators, we spent a long time looking at young stars, which would have young planets, to try and see if we could see them with infrared radiation. A little bit more than 10 years ago, we got our first major success, which is a system of planets called HR 8799. And I apologize for the boring names. They don't let me name extrasolar planets, which is probably good because the names I would give them would not reflect well on astronomy, but also kind of sad because it means they just get catalog numbers. What you're seeing in the center is the light from the star, not perfectly corrected by our adaptive optics. So there's still that lens flare. But the dots around it, labeled B, C, D, and E, are planets orbiting the star. Star's about 50% more massive than our sun. The planets are about 5 times the mass of Jupiter. They have a temperature of about 900 or 1,000 degrees. But those really are extrasolar planets. And a year or two ago, to celebrate the fact that we've had 10 years of studying them, some colleagues of mine put together a movie of this. And what you're seeing here is real data. The star in the center, and then each of those dots represents a planet, and you're seeing them orbiting. just like Kepler hundreds of years ago said they would, or just like Galileo saw when he looked through his telescope and saw the moons of Jupiter. This is a real movie of an entire solar system orbiting around it. And it's really, in my admittedly biased opinion, the most amazing thing I've seen in my career as an astronomer, to see just the same way Galileo saw moons going around Jupiter, we can see a whole other solar system orbiting around its star. Again, bad to compare yourself to Galileo when you're a scientist, although he was confined to his house for a couple of years too. So I'm more and more sympathetic to the complexities of modern science. Um, we can tell from this that the planets are far away from their star. So this is actually a huge solar system, much bigger than our own. We can tell something about how all their orbits line up. And because we can see light from them, we can start to study their composition. We, of course, had our press release and we had our gratuitous image of glowing planets orbiting around a star. And yeah, that's not really what we saw, but we could say it with a little bit of confidence because we could do spectroscopy. Um, Again, I won't go through the spectrum line by line, but we saw things like radiation that we think is from hot, thick clouds of liquid metal in the planet's atmosphere glowing up between the holes in the clouds. We saw the same water and hydrogen. Again, water means 1,000-degree Kelvin superheated steam. We saw carbon monoxide, we saw methane, we saw enough that we could begin to probe the composition of the planet and compare it to our models. So these planets still were found kind of in the outer parts of solar systems, and we'd like to still don't have the ability to see anything like Jupiter, let alone anything like Earth, because there's too much glare from the star. So our next step was to build an advanced instrument we called the Gemini Planet Imager. This is a schematic of it with a human or a Chilean fox for size. It includes an advanced infrared spectrograph. It includes a very advanced adaptive optic system, one of the most powerful ever built, that the group I worked with at Lawrence Livermore National Lab before I came to Stanford put together. Special masks to block and divert the light from the star, a sophisticated mechanical structure, and really importantly, a lot of very sophisticated software to hold it all together. The masks that block the star, you can see on the right here. We focused the light from the star onto a special gold-plated mask with a hole in it, so the star falls down the hole. The planet light gets focused off to the side and becomes detectable in our camera. We put this together in a laboratory at UC Santa Cruz, technically in a clean room, not clean at the time we took this picture, which is why there are all these chaps with beards, Canadians with beards standing near it. We lowered our spectrograph in. It took about a year to put all the pieces together and get the computers working together. Because it was going to be attached to a telescope and move all over the place, we had to test how it would behave under different gravity loads. So we attached a crane to it, cranked it back and forth to different orientations, listened for anything rattling and falling out, just like you might shake a box of electronics to see if there's some loose screws in it. Then we found the loose screws and fixed them and made sure that the whole thing stays aligned to a fraction of a millimeter, no matter what gravity does to it. Has to do the same thing under harsh weather conditions. So we built a giant meat locker around it and chilled it down to -5 Celsius to make sure it would continue to operate, which it did. After a year's worth of testing in Santa Cruz, we packed it up to ship it down to Chile. My small child helped with the process of loading it for its travel to Chile. Put it on a truck, said goodbye to it, which is a daunting prospect to see a multi-million-dollar instrument that you spend 10 years of your life on loaded onto a truck. Can't drive all the way to Chile, so it was also loaded onto an airplane and flown down there. Unpacked at the Gemini Observatory, where on a pre-existing telescope in Chile, greeted by the local wildlife, who were not really all that impressed to see it arriving. Then I flew down and rejoined it and was again glad to see that it had survived its long trip. Craned it onto the back of the telescope. So on the left, you're seeing what a modern large optical telescope looks like. Telescopes can carry different cameras or spectrographs. And so our telescope gets switched out for other spectrographs that are intended to study galaxies or intended to study stars when we want to study planets. You can see it mounted looking up at the back of the telescope here with its outer enclosure, and these blue cabinets contain the computers that run the adaptive optic system. They're actually in cabinets because we don't want the heat from the computers to create any extra turbulence inside the observatory. We had our first light for it in November 2013. Here's the team down in the control room getting ready to make the instrument operate. We spent about a week shaking it down, and of course, there's the wildlife. We looked at planets. This image is a little bit complicated, but what you're seeing is a star hitting that hole, that mask with the hole in it, but glinting a little bit off the edge of the hole, making that bright ring. So that's not real. But down here at about 5 o'clock in the image, that little dot is an extrasolar planet. It's one that we knew about. It's orbiting a star called Beta Pictoris b. So we cheated for our first images and looked at a planet we already knew was there. But we were happy because our images with the Gemini Planet Imager were much better than a previous generation camera, particularly since the image on the right took an hour to make with the most advanced adaptive optic system that existed in 2010. Our image on the left took us 60 seconds to make. And then when we actually spent half an hour and did sophisticated image processing, we could see the planet beautifully, and you could drive a truck through the space between the planet and the star. So that made the team happy, though again, kind of failed to impress the local wildlife. There we go. These days, even before the pandemic, we did stop traveling to Chile. We reached the point where we could operate the instrument remotely with computers in Stanford. So in the physics and astrophysics building, we have a telescope remote control room with more monitors than you could possibly shake a stick at. And we got some local support from our own more local wildlife as we could use the instrument. We put together a very sophisticated data processing infrastructure that automatically takes the images, finds planets in them, tells us what we're seeing, posts messages in our Slack chat. Again, even pre-pandemic, we were pretty oriented towards remote collaboration. I should say this represents the work of a team of about 100 people scattered around a bunch of different universities. Here's a movie of the survey, which started in 2014 and concluded in 2018. We looked at 600 stars in the solar neighborhood. Each dot on the left shows you where a star is located in the sky. The right shows the images. Here's the Gemini telescope, which is just a really beautiful place that I miss visiting more than I can possibly say. As the images of the stars go by, every so often you'll see a little dot that's a planet, and sometimes you'll see, there we go, 51 Eridani, which we discovered using the Gemini Planet Imager, and there it is orbiting over several years around the star. Sometimes you'll also see other things like lines and rings around the 600 stars that we observed. The lines and rings are asteroid belts. It turns out not only can we see planets around other stars, but we can see their asteroid belts or cometary belts. I'm not going to talk about that anymore because there are other people who focus on this research and it would fill up a whole other talk. But it's, again, amazing that we can see the architectures of other solar systems. In the bottom right, you can see an example where there's a very narrow ring of comets and asteroids from which we can guess maybe there's a planet keeping that narrow ring of comets and asteroids in place. But planets. Before we went to Chile, we thought we might find 20. We saw a total of 6 planets with the Gemini Planet Imager, including ones that were already known to exist, but were allowed to count because we didn't cheat. We looked at all the young stars, whether we knew they had planets or not. And we saw 4 things that are called brown dwarfs, which are like 20 to 30 times the mass of Jupiter, that are kind of on the border between a planet and a star. The planets we saw closer to their star, still not Jupiter's, still can't quite get all the way right up against them. But we did learn things. We learned, for example, that planets like Jupiter are rare. No more than maybe 1 out of every 4 stars, at least for sun-like stars, has a Jupiter-like planet orbiting it. Larger stars are more likely to have Jupiter-like planets, maybe 30 to 40% of them. But it's, again, an evidence that our solar system is not the most common kind of solar system in the universe, that we're not the only way to have planets is to have a big Jupiter and a Saturn and a Uranus and a Neptune. We learned that the brown dwarfs are very rare, the objects that are bigger than Jupiter or Saturn, failed stars, and that they're different than planets. Whatever process that formed them is not the process that formed planets. G5 is a beautiful instrument, but as I said, we couldn't quite see planets like Jupiter. We were still limited to sort of planets 5 times the mass of Jupiter out where Saturn is. There's a bunch of factors that do that, including, for example, wind. Our adaptive optic system measures the turbulence in the Earth's atmosphere about 1,000 times a second, and our deformable mirror changes shape 1,000 times a second to correct for that. But by the time it does that, a couple of milliseconds have passed by, and the shape the deformable mirror takes is always late, especially if, for example, high altitude winds like the jet stream are blowing overhead. This is a wind map. The circle shows where the Gemini Observatory is, and you can see the jet stream practically aims right at us in a way that I find rather frustrating. Our computers are good, but they're 10 years old and just not fast enough to keep up with atmospheric turbulence. And we've kind of run out of stars to look at in the southern hemisphere, and we'd like to be at a slightly better site because it turns out to rain a lot. And so we're now in the process of upgrading and moving GPI in an instrument we're going to call GPI-2. The Gemini Observatory is called that because they have two telescopes, one of them in Chile, one of them in Hawaii. And so we were going to start this process this year, but of course, not happening on the timescale we'd like to. But in a year or two, we're going to move GPI to Hawaii. We're going to have to get a new mascot. Currently, we're leaning towards the Nene, or the Hawaiian goose. And we're going to start looking at a whole bunch of new stars. This is actually a project that I'm just serving as the senior curmudgeon on. It's being led by my former postdoctoral researchers, Jeff Chilcote at Notre Dame, Quinn Konopaki at UC San Diego, Dimitri Savansky at Cornell, Christian Marois in Canada. And I'll still be heavily involved in, but it's kind of awesome to watch the scientists who I've worked with over the years reach the point where they're putting together their own project. We think GPI-2, still not going to see Earths, but that we really could see planets the size of Jupiter in Jupiter's neighborhood, and that we'll look at another 300 or 400 stars with greater sensitivity and see what we can discover. Moving beyond that, though, we're going to have to go to space. There's a limit to what you can do with telescopes on the ground. The next thing in space is going to be something called the Nancy Grace Roman Space Telescope. It's designed mostly to do cosmology, to survey huge areas of the sky, to look at galaxies, to trace the expansion of the universe since the Big Bang. But it's going to carry some of the same technology GPI did, even deformable mirrors, coronagraph masks to block starlight, spectrographs, and look at planets. On the left, you can see an image looking at some random star. These are all simulations. The telescope is going to launch for another 5 years. On the right, you can see an image with a planetary system. You probably can't spot the planets, but by comparing and processing the two, we can see planets down to a level of about 100 million times fainter than their star, which for the first time will let us see not young, giant hot planets like HRD 799, but a mature solar system like our own. The Roman telescope can only barely see these Jupiter-like planets. It's only going to look at a couple of stars, but it's the next step to prototype in space the same kind of technology we've been using on the Earth. There's also another way you can look for extrasolar planets in space. So if you want to see something faint next to something bright in normal life, like say there's a bird flying close to the sun, what do? Well, I can't see what you all do, but there's probably a gesture you can make if you're imagining looking for a bird close to the sun, which is you hold up your hand, you block the sun, and you peek around the edges and see what's visible. It turns out that you could try to do the same thing in space. You could have a giant space hand deployed in front of your telescope, blocking the star so that just a little bit of the planet is visible. Of course, NASA doesn't have giant space hand technology. So instead, we use something called a star shade. It's a huge structure that folds up and then deploys into a disk 30 or 50 meters across that maneuvers with respect to the space telescope to barely block the star and let you see the planet peeking around the edges of it. The complex flower shape is set by a lot of details of how light works to try and reduce how much glare leaks around the edges of it. And again, it's something that could fill an entire fascinating talk. Something like this could allow you to take spectra of Earth-like planets. There's a lot of engineering details. You have to line it up with respect to the telescope to an accuracy of better than a meter. When you get bored of looking at a given star, you have to move the formation, the telescope and the spacecraft around, which can take weeks, during which your telescope could go look at something else, like some galaxies for the galaxy people, if it wants to. We've been studying if we could test this technology. A full-size star shade would be a multi-billion-dollar space mission. And so together with a collaborator, Simone D'Amico in the Aeroastro department, we've been looking at a miniature star shade that would be only about 3 meters across. And rather than feeding a huge Hubble-sized telescope, would feed a little telescope that's 10 centimeters across, and would actually operate in Earth orbit with the two telescopes aligning for a few minutes every time their orbits cross the equator so that they can line up and study a star. That wouldn't really see Earth-like planets, of course, but it might prove the technology. So in my last minute or two, I'm just going to talk about the future, where astronomers would like to go with this. As I said, the goal really is to move closer and closer to the star, to smaller and smaller planets, to the point where we can start to study Earths. And there are a couple of proposed space missions that could do that. One of them is called the Habitable Exoplanet Observatory, or HABEX. It's a proposal for a 4-meter space telescope, which is about twice the size of Hubble, which would have both a coronagraph like GPI inside the telescope to block starlight and a star shade that would maneuver with respect to it, block the light from the star. And the idea is that you'd use the coronagraph to find planets, because you can point at lots of stars rapidly, and then you'd slowly move the star shade into position when you want to study one in detail and study its spectrum. And NASA studied it as an example of what a mission that was extremely focused on exoplanet science could do. And the answer in simulation, at least, is it could study 10 Earth-sized worlds that are orbiting in the Goldilocks zone of sun-like stars and get the right amount of radiation to potentially have water on their surface. NASA also studied a bigger mission. Again, we're not very good at names, at least before we fly the missions. And so the mission to launch a large telescope that would study optical and infrared and ultraviolet radiation is called the Large Ultraviolet Optical and Infrared Telescope, or LUVOIR. The LUVOIR concepts are telescopes from 8 up to 15 meters in diameter, intended to study exoplanets, but also a broad range of other astrophysical science. It carries a coronagraph to block the star. It carries a whole bunch of other astrophysical instruments. The telescope is protected by a huge sun shield, not to keep it cold, but to keep it incredibly stable so that the signal from the planet is not hidden by the telescope changing shape as it stares at a star and heats and cools. And to give you a sense of perspective, this is a movie that I made, that was made by the California Academy of Sciences for a talk I did for them once. There's the Hubble Space Telescope. Hubble doesn't really look at Earth, of course. Looking at Earth is frowned upon with telescopes. And here, for size comparison, comes LUVOIR. Seeing the underside of that sun shield and its communication antenna. And as we pull back, you can get a sense of the scale of the missions that astronomers are considering as potential future concepts to look for what it would take to really look for Earth-like planets. Missions like this would be 20 or 30 years off. They would have to be a choice to select them as a national priority. But with technology like this, we could start to study other solar systems, not just giant planets, but Earth-sized planets in that Goldilocks zone around hundreds of stars like the sun in the solar neighborhood. And if we did, we might start to produce images, not just like the 8799 image I showed you, but images like this. There's an asteroid or a comet ring, and there's 5 planets, some of which really are as tiny as the Earth. And again, we could take their light, feed it through a spectrograph, and we'd see not just the spectral features from water, but we'd see spectral features from things like oxygen. And on Earth, we think the reason there's oxygen is because there's life. There are other processes that could produce it. And so when we study other planets, we'll have to be incredibly careful about not over-interpreting what we see. But we are at the point where we could potentially detect worlds with oxygen in their atmospheres and maybe signs of life. I'm actually a bit of a pessimist. I think planets that have life will be incredibly rare, and that even these powerful telescopes may not see any of them or may only see one. But that also, I think, would be a profoundly transformative moment to realize that the Earth is almost unique in our galaxy, and remind us that we better do a really good job of looking after the one Earth-like planet we have. We might discover planets like Earth and life are incredibly common. That would transform us. We might discover that we're incredibly rare. But one way or another, we have the technology to answer this question. Not only are there other worlds like Earth, but is there life on planets out there? And I'm going to stop there. I'll leave this link up with some potential reading. And thank you all again for the opportunity to talk to everybody.
Fantastic. So I know we have a number of questions. One of the questions is it possible that our solar system is typical, but that we just can't yet detect smaller inner extrasolar planets yet? Is that the...
Yeah, that's a really good question. Yeah, as I said, the technology we have is not powerful enough to easily see solar systems like our own. The Kepler mission I mentioned discovered thousands of planets. If every star had had a solar system just like our own, Kepler would have found only 3 planets. It could only barely detect some Jupiters and maybe one Earth. So it's certainly possible that they're hiding out there. If it's true, though, Kepler found so many of these densely packed super-Earth planets that if it's true, then there would have to really be 2 completely different ways of forming solar systems, one that would form Kepler planets and one that would form ours. Because not only haven't we seen our solar system, we haven't even really seen anything close to it. So they could all be hiding out there, and that's really why we need these new missions to answer that question. So maybe we are typical, and the Kepler planets are weird. Yeah, it's always easy to get biased. I saw somebody put this in the question and answer, that if you can only see one kind of fish, you might decide that's the only fish in the universe. So we really don't know. We might be typical. We might be incredibly weird as an outlier.
I'm almost asking about if you could speak about the use of the Lick Observatory in exoplanet research and discovery.
Yeah, like those of us who live in the Bay Area, or of course almost everybody here was at Stanford, you can see Lick Observatory at Mount Hamilton. I spent a huge chunk of my graduate and postdoc career there. I stopped counting at about 200 nights that I spent up at Lick Observatory. It was one of the first places to do, it didn't make the first discovery of extrasolar planets, but it did confirm the first Doppler measurements of extrasolar planets and then discover a whole bunch more. In fact, the scientists who did it could have been the first people to discover extrasolar planets, except they hadn't analyzed their data because they were only looking for planets like Jupiter, which takes years to see a planet like Jupiter. And so they said, well, we've got years to analyze our data. Whereas Mayor and Queloz sort of analyzed their data immediately and said, hey, we can see a planet in only a week. There must be this weird planet. But it definitely was an early place that pioneered both the Doppler technology, and then what I worked on was the adaptive optics. We tested the very first adaptive optics systems used for astronomy on the old Shane telescope up at Mount Hamilton.
Another question that came in is there a consensus opinion about the grand tack hypothesis? And has the study of exoplanets helped us better understand Jupiter's history in particular?
Yeah, so for those who don't know it, something I didn't talk about a lot, but that we realized from exoplanets and from our own solar system is that planets move, that especially early in the history of the solar system, planets like Jupiter and maybe the other giant planets migrated, that they formed in one part of the solar system and then they marched in towards the sun from friction from asteroids and gas and things like that. In the grand tack hypothesis, Jupiter moves in and then turns around. Well, it doesn't really turn around, but it stops moving and then starts moving outward as new frictions and new torques are present. There's some tentative evidence for this being true in our solar system, but it's hard to test, of course, because we don't really know what happened. Our solar system formed 4.5 billion years ago. And so studies of extrasolar planets and of planets, one of the things we're going to do with the Gemini planet imager is try and study planetary systems that are actually forming. We've built it to be sensitive enough to look at solar systems that are only 2 or 3 million years old, which is literally when the grand tack was happening. So we certainly hope that by probing the process of planet formation kind of in real time, we can see whether these complicated models are true or not. And it's definitely true that discovering the weird solar systems has prompted lots of new ways of thinking about the way our solar system formed too. And vice versa, the clues in our solar system help us understand the other planetary systems.
The next question is, can adaptive optics be accomplished digitally without an actual flexible mirror?
It's hard to do anywhere near as well. So we all see, TV shows where they click on the enhance button and suddenly the image gets 100 times sharper. And it's not mathematically impossible, but to do that, you have to have essentially perfect understanding of, say, how the atmosphere blurred what you were looking at, of the sensitivity of your camera, and you have to have no noise. When you're correcting for something like that, you could think of it as correcting for how much the image has been attenuated by the Earth's atmosphere, which is like it's been divided by a very large number. You're correcting for it by dividing by a very small number to get back to the original image. And if you get that even slightly wrong, dividing by the wrong very small number can massively amplify the noise in whatever you're looking at and give you a fairly crazy image. So people do use techniques where they use cameras that take incredibly fast images and computer processing, but it's never as good as the adaptive optics, and it really isn't sensitive enough to do anything like an extrasolar planet. But you can do a lot of it on your backyard telescope, and there are lots of good resources for trying this at home.
Maybe people can write in and let us know if they've done anything. The next question is, how can a deformable mirror change 1,000 per second? What is it made of?
Yeah, if I was in my office, I would hold one up, but it's sitting in my office where I can't get to it. So they're very thin sheets of glass, about 1 millimeter thick. Behind them are little electrostatic actuators, bits of material that when you put a voltage on them expand and contract. And it doesn't change shape by very much. You can't see this with your eye. The total amount of change of the surface shape is much less than the width of a human hair, but glass is flexible enough that you can bend it just that little extra tiny bit. That's the conventional technology. What GPI actually uses is a silicon version of this. So you can take a piece of silicon, micro machine it so that it will also bend up and down and then coat a gold layer on it so that it's a nice shiny mirror. It's actually very similar to the technology that's used in projectors that you plug into your computer for home theater or for when you're giving talks like this in person, except much more precise, much more expensive. Our mirrors are sort of $1 million items, but equally compact. And so the glass mirrors that we used to discover HRD 799 were about this big across. The mirror that we would have needed if we'd used glass mirror technology for GPI would be about this big across, which would be challenging to put inside our box-sized instrument on the back of the telescope. The silicon mirror is about this big across.
The other question I think you had seen in there was following along Arthur Eddington's parable of fishing with a net and concluding there are no fish smaller than the size of the gaps in the net. To what extent do planet detection methods bias what we can conclude about distribution of size and distance of planets? Example, easier to detect large planets near small stars?
Yeah, it's similar to the question of could solar systems like our own be hiding because we don't have the technology to see them. And that does create uncertainties when we try to estimate the number of planets like Earth that are out there, which is something astronomers are spending a lot of effort on because we'd like to know we'd at least like to know, have a guess as to how many Earth-like planets there are before we launch the giant space telescopes into space to look for them. We do have to extrapolate. We have to correct for the fact that we couldn't see Earths, but we could see planets 50% bigger than Earth or 50% closer than Earth, and can we extrapolate out to the number of Earth-like planets? So we do try to account for that and correct for it, but if we're being honest, we would admit that that leaves a tremendous uncertainty because we don't quite have the right technology to see Earth-like planets there. Or similarly, I said, based on GPI, no more than 25% have stars have planets like Jupiter. Well, we can't actually see a planet just like Jupiter with GPI, so I'm extrapolating. I'm guessing that out in the outer parts of solar systems, we don't see very many giant planets. In the inner parts of solar systems, they see some number of giant planets, unless all the giant planets are hiding right in between the outer range of the transit guys and the inner range of GPI. Giant planets are probably pretty rare, and the universe would have to be really mean to hide all the giant planets right where we can't see them. But the universe is mean sometimes, so it's possible that when we build GPI-2 and as our Doppler and transit colleagues improve their technique, that we will discover solar systems like our own are much more common than I thought.
Do planets in other solar systems all rotate in the same direction as in ours? And if not, what determines the direction of their rotation?
That's a good question. I mean, the solar systems are all fairly randomly tilted with respect to each other. There's no particular law that orients them with respect to the galaxy. But an interesting version of that question is, in our solar system, all the planets do go around the same way in this one nice flat, relatively flat solar system. And that's one of the things we're trying to determine with our images, like the movie I showed you of HRD 799. Are all 4 of those planets aligned with each other? They are clearly all going around in the same direction, but maybe still their orbits could be tilted with each other. And that would be weird because we think the way the solar system formed out of a gas of disk and dust, you get a nice flat solar system. So that's actually something we're trying to study, is how flat are other solar systems compared to our own? Do all the planets go around in a nice, well-behaved circles like our solar system, or on they crazy tilted orbits all over the place?
Would you be able to talk about the possibility of life in other planets and the techniques used to detect biosignatures?
So a biosignature is a word we use for some signature that's the presence of life. With other solar systems, the only way we're going to see that really to start with is by studying the atmosphere of the planet. And so we want to look for something in the atmosphere that's associated with life. On Earth, that thing is oxygen. As you probably know, in the early history of Earth, the atmosphere had almost no oxygen in it. It was produced by the first blue-green algae, by plants that broke carbon dioxide down to create oxygen. And it's only sustained by the presence of life. If all life on Earth vanished, the oxygen would get locked up inside rocks. It would be combusted. It would be absorbed into other materials. The oxygen would vanish out of our atmosphere on timescales of a few million years. So our atmosphere is not in what a chemist would call equilibrium, in balance. Our atmosphere is way out of balance because life. And so the first thing we're going to look for, if we can, is that oxygen signature around other worlds. But the universe can surprise you. And people have also said things like methane is a signature of life. There's tentative evidence for methane being present on Mars. It's very tentative. We obviously don't know if it's caused by life or not. I would bet not. Even though we've got like robot trucks driving around on the surface of Mars, we can't figure out if there's life there or not. So when we see our spectrum of other planets around other stars, just because there's oxygen, you shouldn't believe it. And what we're going to do is we're going to try and look at every chemical in their atmosphere and try to create models that say, we can't explain having simultaneously carbon dioxide and water and methane and carbon monoxide without life. But it's still going to be a tentative and indirect discussion. And I think people are still going to argue about it the way we're still arguing about it on Mars years and years and years later.
Mm-hmm. So another question is, wouldn't it be better to build a huge telescopes on the moon rather than in space?
People discuss that. I honestly think I would rather build a huge telescope in space. The moon is dusty, and you don't want dust on your telescope. And the moon has gravity, and gravity is actually a real nuisance because it makes your telescope mirror kind of bend. The pictures of the telescope you saw sort of briefly of the Gemini telescope, that's 200 tons of steel, 1,000 tons of concrete, all of which exist just to hold about a gram of aluminum in the right shape. The thing that actually does the reflecting of light is basically a soda can's worth of aluminum, held in place by tons of glass, hundreds of tons of steel, thousands of tons of concrete, all of which is there just because of gravity. And so if you build a telescope in space, no gravity. So telescopes can be much more lightweight and precise than they would if you put them on, say, the surface of the moon. So I think actually it's nice to get away from into free space.
Second to last is, what is the influence of machine learning software on current detection, et cetera? Like, for example, helping with atmospheric interference. Yeah. How will such artificial intelligence have more influence in the future?
It's a good cutting edge area. I mean, I mentioned the fact that our adaptive optic system is always a millisecond late keeping up with turbulence. That sounds like a machine learning problem to try and predict what's going to happen a millisecond in the future. So it's definitely something that my students and collaborators want to work on, and that other groups are working on, predicting the atmosphere into the future. Or, the images I showed, they're dots and blobs all over the place. Which one's a planet? That sounds like a machine learning problem. And so we're exploring using machine learning to improve the adaptive optics and to find the planetary signatures.
And the last question I have for you is, can you speak to the strangest anomaly you have come across?
I mean, personally, I think seeing that 4-planet HR 8799 system. So there's a long history. When you see the dots, you think, oh, I found a planet. And then it turns out, no, it's actually just another star. You have 2 stars, one of which is a long way away, and they just happen to look like they're lined up by chance. And you get incredibly excited and think you found a planet. Then you study it carefully. You look at how they're moving, you look at their spectra, and you say, no, I found a background star. I spent 10 years doing that. I found 100 background stars. And then Christian Marois, my collaborator and friend and postdoc, he found this star and he said, I found not just one, but 2 candidate planets next to it. I'm so excited, he said. And I said, great. We're never going to find 2. If there's 2, they absolutely have to be background stars. I actually said that was going to be Macintosh's law. Anytime you find 2, they're background stars. But we did due diligence, and we went and looked at the system, and he proved that they were moving and orbiting. And then he found a 3rd one, and then he found a 4th one. And so the fact that we went from 0 to our first discovery was this beautiful system of 4 planets. And like I said, now we can see this movie is just like the most utterly amazing thing. And it's a really weird system. We've never seen anything like it again, which is kind of what always happens. Your first discovery is the most awesome one. So that's definitely our version of the weirdest thing we've seen, looking for planets with our telescopes.
Awesome. Bruce, thank you again so much for joining us today and sharing your expertise and research. It has been absolutely fascinating. Thank you.
Thank you all for listening.